In the last section of the book, we started with kind of the easiest application, or a fairly easy application. We looked at displacement given velocity. You integrate velocity to get the displacement. You integrate the absolute value of the velocity, the speed, to get the total distance traveled. This section of the book is another fairly easy application. We're going to talk about area in the plane, so the area trapped between two curves in the xy plane. We've interpreted the integral as area under a curve and above the x-axis, or if the curve goes below the x-axis, then area above the curve and below the x-axis. But now we want to look at the more general problem of, we've got y equals f of x, y equals g of x. How do you find the area trapped between those two curves? As we'll see, once again, absolute values will come into the formula. You can write a nice simple formula by putting absolute value signs in, but that doesn't really save you from doing the work. It's just a nice way of writing it quickly. But at the end of the day, you still have to find out when the thing inside the absolute value signs is positive and when it's negative to actually evaluate the integrals that we do. So let's look at an easy example. Let's take a parabola, and I'll just assume this is y equals x squared, and take the line y equals 4, and let's find the area. So those would intersect. Well, you'd need 4 to be x squared, so x would be plus or minus 2. So this would be minus 2, this would be plus 2. And then let's look for the area trapped between those curves for x between 1 and 3. So here's 1, here's 3. So we would like to find this area, that total area. Okay, well, there are a couple of things we could do. I'll first discuss the one we're not going to do, and then we'll look at the other one. What you could do is, since we've already talked about area under graphs and above the x-axis, what you could do is between 1 and 2, you could look at this rectangle below y equals 4 and above the interval from 1 to 2, and subtract the area below the curve y equals x squared and find that remaining area, the area that's between below y equals 4 and above y equals x squared. So we could do that. So we could do, so what did I say? You take the area below y equals 4. Yes, it's a rectangle, so we know it's just the height times the width, so the area is 4. But writing it in terms of an integral, we could say, oh, it's the integral of just the constant 4 with respect to x, as x goes from 1 to 2. And yeah, that does come out to be 4 times x evaluated from 1 to 2. So 4 times 1. So 4. Great. And that would give you the area of the rectangle. And you would subtract the area below the curve y equals x squared. So that would be the integral of x squared from 1 to 2. So you could do that. And then you could subtract. And kind of undoing what we usually do when we evaluate integrals. We have this more complicated one with the subtraction in it. We split it up into pieces, but now just to make a point, I'm saying, well, we could think of this as subtracting the integrals or the integral of the difference. And what I'm going to say, what we want to see, is that this is a better way to think of it than as the difference of two areas. But let me do the other part first, look at the other part first. So we could do that for this part of the area, and then for this part of the area, we would do the analogous thing, or we could do the analogous thing. You can take the area, completely below. You could take the area completely below y equals x squared and get all of this, and then subtract that rectangle that's missing. So between 2 and 3, what you could do is you could take the integral from 2 to 3 of x squared dx and then subtract the missing area from the rectangle, which we once again will, instead of using a nice easy formula for a rectangle, write in terms of an integral, so that we can subtract and get the integral from 2 to 3 of x squared minus 4 dx. So this integral would give us that area, and the other integral would give us this other area, and then we would add them. So what we want to look at is the integral from 1 to 2 of 4 minus x squared dx plus the integral from 2 to 3 of x squared minus 4 dx. Now we can calculate these easily, and I will, but I want to say something else first. There's a reason to look at these integrals like this instead of as separate, one area minus another area. And one of the reasons is psychological, and the other reason is more practical. So let me draw a bigger picture of just this part so that I can draw something else that I want to draw. So first, let me go over the psychological reason why you'd prefer to integrate the difference of these two functions instead of finding the difference of the integrals. There's kind of philosophically, there's no reason you should worry about what's down here at all. You should be finding the area between these two curves, and if you're thinking infinitesimally, as we talked about for definite integrals, what you should think of is taking a small rectangle trapped between those two curves. What should its width be? Its width should be a little change in x, but we think an infinitesimal little change in x, dx. So you should think an infinitesimal change in x, dx. What's the height of that rectangle? The height of that rectangle is exactly this y-coordinate minus this y-coordinate. It's 4 minus x squared. So the height of that infinitesimal rectangle is 4 minus x squared, where it's some x coordinate. So you get a bunch of infinitesimal little blobs of area. A little blob of area trapped between the curve. A little dA is 4 minus x squared dx, the height times the width, and then a definite integral, the continuous sum of all the infinitesimal little blobs of area. So yeah, that's what you get. You integrate as x goes from 1 to 2 of 4 minus x squared dx. On the other piece of the integral, you do the analogous thing. The curve y equals x squared has passed above the line, so but still, over here, you take an infinitesimal little rectangle. Think of it as a rectangle of infinitesimal width dx, and its height will be the top y-coordinate minus the bottom y-coordinate. But now the top y-coordinate is x squared, and the bottom y-coordinate is 4. So this is height to find that integral, you add up all the infinitesimal little blobs of area, but an infinitesimal chunk of area here is the height, x squared minus 4 times the width, dx, and the integral you should think of as the continuous sum of all of those little pieces of area. Great. So, okay, that's kind of psychological. That's why you should just think of these little rectangles, not taking this whole, the area of the whole top and subtracting the whole missing area. Why is it better to think of it as integrating the difference for a practical reason? Well, we used fairly easy functions, but we could have used more complicated functions. Something like, we could have let f of x be, maybe one of our functions is, instead of 4, it's 4 minus or plus e to the negative x squared. And instead of x squared, we had x squared plus e to the minus x squared. And you want to find the area in between these two curves. Well, yeah, so it's true. You could kind of integrate, this one and subtract missing area below the other one, or you could integrate the difference. Does it matter? Yeah, it matters. We can't integrate e to the minus x squared. It doesn't have an elementary antiderivative. So we couldn't do these separate integrals. If we had here, instead of x squared, we had x squared plus e to the minus x squared dx, we won't be able to do this integral. And if you had here 4 plus e to the minus x squared, you can't do this integral either. But if you subtract the two integrals, the part that we can't integrate gets wiped out. The e to the minus x squareds cancel out, and you still just get x squared minus 4. So this is a practical reason why you'd prefer to integrate the difference, because some bad stuff might cancel out in the two functions. All right. So what are we getting? We're getting that we have two functions. I'm letting f of x be 4, not the 4 plus e to the minus x squared, but it wouldn't matter because that part would cancel out if I also made gx squared plus e to the minus x squared, but I'm not. We're looking at these two functions, and we want the area trapped between their graphs for x between some values a and b. We picked 1 and 3 initially. And what we saw was that when f of x is bigger than g of x, so when 4 is bigger than x squared, when f of x is bigger than g of x, you want to integrate 4 minus x squared. So that's why we got the integral from 1 to 2, a 4 minus x squared dx. But then we needed to add to that the area from over here, but now x squared is bigger, so we take x squared minus 4 from 2 to 3. Is there one nice formula? So this is if 4 is bigger than x squared. Another way of saying that is that 4 minus x squared is greater than or equal to 0. So that's the same as saying 4 is greater than or equal to x squared over here. In this, we used x squared minus 4 when x squared minus 4 is greater than or equal to 0. What's the same thing? This is when 4 minus x squared is less than or equal to 0. So if 4 minus x squared is greater than or equal to 0, you integrate 4 minus x squared. If 4 minus x squared is less than or equal to 0, you negate it and integrate negative that quantity. Can we write that all in one nice formula? Yes, with absolute values. And this is kind of what we did when we had the total distance traveled. We said, okay, you split it up, you look at where the object's moving in the positive direction, where it's moving in the negative direction. If you want to write in one nice integral formula, you use absolute values, but then to evaluate, you actually have to split up anyway. Well, the same thing's true here. So what's the area between the graphs? of y equals f of x and y equals g of x for x in some interval. This, the nice way to write it, one quick formula, you take the absolute value of f of x minus g of x. That gives you a height. That gives you the height of the little rectangles between the two curves, regardless of which one is bigger. If f of x is greater than or equal to g of x, then the absolute value will just be f of x minus g of x. If g of x is greater than or equal to f of x, the absolute value will be g of x minus f of x. So you're always taking the distance between the top graph and the lower graph. You take this absolute value, that's the height, you multiply times an infinitesimal little change in x to get the width. This gives you a bunch of little rectangles, a bunch of infinitesimal rectangles, and you take the integral, the continuous sum of those as x goes from a to b. All right. So that's the nice formula that you write. Does it help you calculate it? I mean, not any more than having it split up in the first place. We still have to split this integral up into pieces where f of x minus g of x is positive. So that's where f of x is greater than or equal to g of x. Or when I say positive, well, I was allowing for equal to 0. So we split it up into where f of x minus g of x is greater than or equal to 0. So f of x is greater than or equal to g of x. And where f of x minus g of x is less than or equal to 0. So that's where f of x is less than or equal to g of x, so that we can get rid of the absolute value sign so that we can integrate. So what do? Well, you do what we just did. So let's pretend that we hadn't just discussed it, we didn't already have it split up, and you were just asked, oh, what's the area between the graph of y equals 4, the graphs of y equals 4 and y equals x squared for x between 1 and 3. Pretend we hadn't drawn the pictures, pretend we hadn't split up the problem already. What could you write quickly? Well, if you want to write one quick integral that gives you that area, it's the integral from 1 to 3 of the absolute value of 4 minus x squared times dx. Great. In a way, that's just kind of a nice notation to write, but to calculate anything, you have to split this up. To evaluate this, we need to know where this quantity inside the absolute value signs is greater than or equal to 0 when it's less than or equal to 0, so that we can deal with the absolute value signs. So what do? We need to know. You do what we did when we were calculating the total distance traveled. You want to know where a continuous function, 4 minus x squared is continuous, is positive and where it's negative. You find out where it's 0, and then you check the regions in between the zeros and see whether the function's positive or negative. So you find where 4 minus x squared equals 0. Well, we know where that happens. So that's where x is plus or minus 2. It's where the graphs intersect. It's the x-coordinates where the graphs intersect. But you can just solve this. It says x squared equals 4, so x is plus or minus 2. We only care about the interval from 1 to 3, so we don't really care that one of those occurs when x is 2. We've got, here's the real line. Here's 1, here's 3, here's 2, here's 2, and 4 minus x squared is 0 at 2, and the only other place it's 0 is way down here at minus 2. So we want to know between 1 and 2, is the function positive or negative? It has to be one or the other. the whole time. It can't switch signs. So if it switched signs in between here, it would have to pass through 0 by the intermediate value theorem, since 4 minus x squared is continuous. But there are no other zeros in here, so it can't switch signs. So just check it 1, for instance. When x is 1, 4 minus x squared is 3, that's positive. So it's positive in here. 4 minus x squared is positive between 1 and 2. And between 2 and 3, just pick anything between 2 and 3, but for that matter, you can pick 3. Because the sign doesn't change for any x greater than 2. It only could change at plus or minus 2. So just put in 3. You get 4 minus 9, that's minus 5, that's negative. So yeah, 4 minus x squared is positive between 1 and 2 and negative between 2 and 3. All right, so what does that mean you do? Now you've found, so we just found 4 minus x squared is greater than or equal to 0 on the interval, I'll say this, on the interval from 1 to 2, and 4 minus x squared is less than or equal to 0 on the interval from 2 to 3. So what do you get? We're trying to integrate, or we are integrating, from 1 to 3, the absolute value of 4 minus x squared dx. We split it. We split the integral, the interval that we're integrating up. We split it where we had to split the interval here. So that's at 2. So you write this as the integral from 1 to 2 of the absolute value of 4 minus x squared dx, plus the integral from 2 to 3. I'll say it again like I said it when we were looking at distance traveled. You can always split up integrals like this. Right? Take the integral from 1 to 3 and first go from 1 to 2, then go from 2 to 3 as long as you don't change the integrand. And we didn't. It's 4 minus x squared. But usually this would just give you 2 integrals in place of 1 and there'd be no point. But when your formula, kind of your algebraic formula, the expression you know how to integrate is, or you want to know how to integrate is changing, then you need to split up the integral. Because when 4 minus x squared is greater than or equal to 0, well, that's what's true between 1 and 2. And when something's greater than or equal to 0, its absolute value is just itself. So we get this. But when 4 minus x squared is negative, the quantity 4 minus x squared is negative, its absolute value is negative the quantity. So you get this, and this is x squared minus 4. So we were pretending that we hadn't already broken this up into pieces and looked at it, but yeah, we're back where we were at the beginning of our discussion. Yeah, between 1 and 2, you integrate 4 minus x squared. Between 2 and 3, you integrate x squared minus 4, right? You distribute this minus sign, and you get this. And then you just do this. So we can do it. These aren't hard integrals. You get 4x minus, use the power rule, minus x cubed over 3, evaluated from 1 to 2, plus, then you get a minus 4x plus x cubed over 3, evaluated from 2 to 3. And so we get, you plug in 2, and you get 8 minus 8/3 minus what you get at 1, which is 4 minus 1/3. And you add to that what you get at 3, which is minus 12 plus 27/3, so plus 9. And then minus what you get at 2. So minus what you get at 2, which is minus 8 plus 8/3. And you put all that together, and I think you get something nice. Let's see. Let's distribute all the minus signs. So we get 8 minus 8/3 minus 4 plus 1/3. I'll just go ahead and write this as minus 3 plus 8 minus 8/3. Okay, so here's an 8 and an 8. That's a 16 and a minus 7. So there's a 16 minus 7, so I get 9. And then I get minus 16. So that all the integer parts are giving us 9. And then all the thirds, there's a minus 16/3 plus 1/3. So that's minus 15/3, also known as minus 5. 4. The area was 4, clearly. All right, that's what you do. We kind of did this problem twice. We started out with it split into pieces, and then I discussed writing it in terms of absolute values, and after we wrote it in absolute values, we used writing it that way to split it back up into pieces. So it may have seemed like this took a long time. It doesn't really take this long, but yeah, let's do another example. Let's take a slightly harder pair of functions. So let's see, there were two I specifically wanted to use. So another example. So suppose f of x, so find the area between the graphs of y equals e to the minus x plus e to the x squared and y equals e to the minus 3x plus 4 plus e to the x squared for x between 0 and 3. All right. You might try to draw a picture of this or have your calculator or computer graph this. You'll run into significant trouble if you do that. You won't see much because this part, the e to the x squared, gets so big so fast that you'll have trouble seeing the difference between the two graphs. There won't be a good scale. The good news, that's the bad news. It's going to be hard to picture this, although there are some things we could do. But we could picture the difference where the e to the x squareds cancel out. But the good news is you don't need to picture it. Right? You don't need the graph of this to do the problem. We know how to find the area. The area that we're looking for will just be the integral from 0 to 3 of the absolute value of the difference. So this one minus this one. The e to the x, or we're the other way around. We're taking absolute values. The e to the x squared terms will cancel out, and you just need to integrate the absolute value of e to the minus x minus e to the minus 3x plus 4 with respect to x. This is what we need to do. What's our main problem with this? Well, we have 2 or 3 problems, depending on how you count. We need to find out where this quantity is positive and where it's negative, so we can deal with the absolute value signs by either getting rid of them or negating. And we also need to know, once the absolute value signs are gone, we would need, or replaced with a minus sign, we'll need to know how to integrate e to the minus x and e to the minus 3x plus 4. You do both of those with substitutions. So I'll get to that part second. I'll do that part second. Right now, why don't we figure out where this function's positive and where it's negative. So this is a continuous function. Where does, we find where it's 0, where does e to the minus x minus e to the minus 3x plus 4 equals 0? Well, put one of these on the other side. I'll put the e to the minus 3x plus 4 on the other side. This is where does e to the minus x equal e to the minus 3x plus 4? At this point, you either use that the exponential function is 1 to 1, so for these two things to be equal, their exponents would be equal, or what's essentially the same thing, take natural logarithms of both sides. One way or the other, you get that for these two things to be equal, their exponents have to be equal. So we need minus x to equal minus 3x plus 4. Add 3x to both sides, you get 2x equals 4. So x equals 2. So that function is 0 when x is 2. And that's it. So here's a real number line. At x equals 2, we get 0 for the value of e to the minus x minus e to the minus 3x plus 4. So if x is, for all x is less than 2, this function is either always positive or it's always negative. For all x is greater than 2, this is either always positive or always negative. What's my favorite number less than 2? 0. So plug in x equals 0. When you plug in x equals 0, you will get, so when x is 0, you get 1 minus e to the fourth. Well, e to the fourth is big. It's a lot bigger than 1. So this is negative. So we get something negative over here. When you might suspect that the sign has to change when you pass through 0, that's not true for all functions. We kind of expect it, but it doesn't have to be true. So we really do need to check this. What's another nice x value to plug in? I don't know, x equals 3. Maybe plug in x equals 3. You get e to the minus 3 minus e to the, okay, when x is 3, you get minus 9 plus 4, so you get minus 5. E to the minus 3 over e to the minus 5, maybe it would look better as 1 over e cubed minus 1 over e to the fifth over e to the 5. E raised to the fifth power is much bigger than e cubed, so this is a smaller positive number. So this is then 1 over e cubed, so this is positive. So yeah, the sign did switch here. You get a plus. So what does this mean for our integral? It means when x is less than 2, this thing inside the absolute values is negative, which means that the absolute value of it is negative, what you're seeing there. So that we break this up at x equals 2. We go from 0 to 2. And from 2 up to 3. And the whole point of that positive-negative calculation is that when x is between 0 and 2, this quantity is negative. So its absolute value is negative, what's in here. So you get this, and you can distribute that minus sign, so you get this plus, you get plus this minus this. So, right, I'll go ahead and do that. But you get minus this plus this. And for x between 2 and 3, this quantity is positive, so that the absolute value is just the thing itself. So you integrate this. Okay, so now we know how to split up the integral. And if we could just integrate these two functions, with the plus or minus signs, it doesn't matter. We could just, if we could produce antiderivatives, then we'd use the fundamental theorem and plug in the top limit of integration and get what you get when you subtract what's at the lower limit of integration and then do it again. All right, so it's good to recall how to do these things. How do you integrate something like that? So how do you find an antiderivative? So we want to find antiderivative. Don't think I've forgotten that we had a definite integral. Right now I'm just doing kind of a side problem. I'm not writing a definite integral, I mean an indefinite integral. I mean, what does most general antiderivative of this look like? And we also want to find antiderivative of minus 3x plus 4 dx. Well, notice that we could do both of these at once if we write a formula for what's the integral of an antiderivative of e to the ax plus b dx, where a and b are constants. So, okay, well, what do? You make a substitution. You let u be, so maybe I'll do it down here. Let u equal ax plus b. So then du, the differential of u, is a times dx. So it's the derivative of this side times dx. The derivative of this side with respect to x is a times a dx. Or what's the same thing, dx is 1 over a times du. And then you use that to change your integral from one involving x to one involving u. So the integral of e to the x plus b, a to the x plus b is u. So you get e to the u. dx becomes 1 over a times du. Ah, yeah, I should have said a is unequal to 0. We are dividing by a, so we better be assuming a is not 0. 1 over a du. You pull out the 1 over a, it's a constant. And then the integral of e to the u with respect to u, just e to the u plus c. And then you put back in that u is ax plus b. So you get this. So what does that mean here? In this case, the a would be minus 1 and b would be 0. So we get 1 over minus 1 e to the minus x plus c. Of course, 1 over minus 1 is just minus 1, so we get minus e to the minus x. And then this, the a is minus 3 and the b is 4. We get 1 over minus 3 e to the minus 3x plus 4 plus a constant. And then you apply those two formulas, the e to the x one in this part, and the e to the minus 3x plus 4 one here and here, and you plug in the number, you plug in 2, subtract what you get at 0, plug in 3, subtract what you get at 2, and add. You get you get whatever you get. You know, the number, it's good practice to go ahead and do it, but really, the actual number that we get is not so important. So rather than calculate that, I'd rather spend my time doing a minor variation on it. What's a slight variation of this problem? Well, we could ask for the area between the graphs. Well, we could say for all x, but how about for all x greater than or equal to 0? So all the way out to infinity. So just all the x's greater than or equal to 0. What would change in this problem? Well, we would change this. The area from 0 to infinity. Does this have to exist? Certainly not. It's an improper integral. Well, in general, improper integrals don't have to exist. This one either does or doesn't, and it does. I know that because I picked an example where it would exist, but just as a general principle, improper integrals like this, when you integrate out to infinity, they could diverge. The integral might not exist. But what would change in what we did? Not terribly much. You integrate from 0 to infinity, and you can split that up into, it's still true that our work before said the sign changes at 2 and only at 2. So you would integrate this from 0 to 2, and here you would integrate from 2, not to 3, but from 2 to infinity. I should say something else. if we assume we've already done the other problem where we integrated from 0 to 3, you could split this up a second way. Instead of going 0 to 2 and 2 to infinity, if you already have done the integral from 0 to 3 of this absolute value, then you could split this up at 3 and take the answer you get from the last one from 0 to 3, and then once x is greater than or equal to 3, we know that the term inside the absolute value signs is positive, and then from 3 to infinity you would integrate this part. It's not necessarily better one way or the other. I want to remind you what this improper integral means, and then I will calculate these, since I didn't do the other ones. I want those. So, what do we get? We get, all right, I'm going to use both of these formulas up here, but drop the plus c's because we have a definite integral. So you get e to the minus x minus 1/3 e to the minus 3x plus 4. And that is evaluated from 0 to 2. Just checking, yes, okay. And then that integral to infinity means you take the limit as b approaches infinity of the integral from 2 to b of e to the minus x minus e to the minus 3x plus 4 dx. Right? Remember, that's what the improper integral means. You take that limit, and let's see, we can go ahead and do this. You plug in 2, you get e to the minus 2 minus 1/3 e to the minus 6 plus 4 e to the minus 2 minus what you get at 0, which is e to the 0, that's 1, minus 1/3 e to the 4th when x is 0, minus 1/3 e to the 4th, plus what we get over here. And what's this? Plus the limit as b approaches infinity. And now we have to use these antiderivatives up here again. Antiderivative e to the minus x minus e to the minus x. Antiderivative of this part is minus 1/3 e to the minus 3x plus 4, but we have a minus that, so minus minus plus 1/3 e to the minus 3x plus 4. And this is evaluated from 2 to b. And so we get e to the minus 2 minus 1/3 e to the minus 2. Is that really what you get? Yeah, okay. Well, that's nice because, okay, this is 3/3. This is 3/3 e to the minus 2 minus 1/3, so we can just write this as 2/3 e to the minus 2. Then there's a minus 1 plus e to the 4th, which is much bigger than those other terms, plus the limit as b approaches infinity of, you put b in here, you get minus e to the minus b plus 1/3 e to the minus 3b plus 4 minus what you get at 2, which is minus e to the minus 2 plus 1/3 e to the minus 2. We get this. What's the big deal? Great, so here's another, this is just some number. Does this limit exist or not? The limit as b approaches infinity of this part. Well, this part's just a number, but as b goes to infinity, negative b goes to negative infinity. And e to the negative infinity, think e to a negative huge number. That's 1 over e to a huge number. That's very close to 0. And as b approaches infinity, so that this exponent goes to negative infinity, and you think 1 over e to the infinity, that's 1 over infinity, that's 0. So this part goes to 0. Same thing happens here. As b goes to infinity, minus 3b goes to negative infinity, plus 4, it still goes to negative infinity. So you once again get e to the negative infinity, which goes to 0. So you're left with this part, this whole part goes to 0. So yes, the area exists. You get a number, it's finite. You get 2/3 e to the minus 2 minus 1 plus e to the 4th. And then there's a minus sign left here. So a plus e to the minus 2 and a minus 1/3 e to the minus 2. Again, this is minus 3/3, so plus 1, minus 2/3, minus 2/3, so another plus 2/3. So it looks to me like we get the fairly reasonable looking answer. 4/3 e to the minus 2 minus 1 plus e to the 4th. These terms are almost negligible. The e to the 4th is much larger than either one of those. Anyway, that's all you do. I kind of incorporated finding areas between curves with integrations by substitutions and improper integrals because that makes the problem more interesting. But the actual problem of finding the area in between two curves, it's easy. You integrate the absolute value of the difference of the functions that you have the graphs of, but that means you need to know where one function's bigger than the other so that you can split the absolute value signs up into the pieces, or split the integral up into pieces where you can deal with the absolute value signs. Next time, in the next section, we're going to do something harder. It'll seem like the first section of applications. We're going to look at distance traveled and lengths of curves, but now they're going to be curves in space or in the plane. We're going to have, think of a particle or some object traveling in the plane or traveling along some weird curve in space, and you'd like to know, and you've got its velocity at each time or its speed, and you'd like to know how far did it go. So that's going to make us use some vectors. We'll have to do like just a small amount on vectors, but it won't be too bad, but it'll be worse than the distance traveled in a straight line. So we'll do that in the next section.